Let's talk about volcanoes. Volcanoes are exciting and mysterious and dangerous, and lots of people are interested in them. I have here a picture of several different kinds of volcanoes. The two on the left are actually the exact same volcano. In one phase, it's spewing out hot lava and what we call bombs, or big blocks of rock. And in this picture here, it's spewing out gas and ash. This is known as Anak Krakatoa, which is baby Krakatoa, named after the large eruption in 1883 of Krakatoa. This volcanic eruption was so massive and explosive that apparently the sound was heard 3,000 miles away. That's the distance from the East Coast to the West Coast across the United States. And then this little baby popped up where that volcano had once been in 1927, and it's been erupting on and off since then. On the right-hand side, I have a picture of the 1980 eruption of Mount St. Helens, a little closer to home here. And then on the bottom, this is a student that was on a field trip with me in Hawaii. And what you can see is she's actually using a rock hammer and some very important asbestos gloves to actually play around a little bit with the lava. So one of the things we're going to talk about is how do you know if a volcano is going to erupt, such as the one on the right, or if you can actually walk right on up to it. Here are the learning outcomes for Unit 7. Go ahead and pause the video and write these down. This particular video is going to concentrate on points 1 and 2 here. So why study volcanoes? Well, besides the fact that they're cool, they occur throughout Earth's seas and continents. And in fact, about 500 million people currently live in the shadow of an active volcano, so they're at risk. And someone's calculated that almost 250,000 people have been killed by volcanic eruptions since the 1700s. And then understanding volcanoes also helps us understand related processes such as global warming, because carbon dioxide is one of the gases that comes out of volcanic eruptions. So volcanic activity is tied to other things. And it's fun and splashy. Okay, so what is a volcano? Well, I think you can all picture a volcano in your mind. Sometimes it's hard to write down a definition. But a volcano is basically a landform. It's a shape. And it's, in some cases, a cone shape, like these two images shown here. And that cone shape tends to happen because of repeated volcanic eruptions that continue to build and build. So it's a landform built by repeated eruptions, and this landform also has lava, ash, and or gases escape from it. So why does magma rise from deep below the Earth towards the surface? Remember, the Earth is pretty much mostly solid. But when there is magma created, it rises, as shown in this cartoon on the right. And that's because magma is less dense than solid rock. So if you threw a rock into a lava lake, the rock would sink. So magma is sort of like oil when you make a salad dressing. It rises to the top. Now, where does the magma come from? We've talked about this, and let's review. Melting occurs at depth for 3 reasons. There's either an increase in temperature, a decrease in pressure, or the addition of volatiles. So let's look at each of these. Temperature increases occur when mantle plumes reach the surface with hot material, such as shown in this cartoon here. Once mantle plumes reach the surface of the lithosphere, they punch through and they create what we call hotspot islands. Here's a picture from your online textbook, and this is showing a mantle plume feeding the Hawaiian Islands. And remember, the plume, we believe, is fairly stationary, and the plate moves over it. In this case, the Pacific plate is moving from right to left, and our most recent active volcanoes are over here, and then other volcanoes that have moved off the hotspot source are shown over here with their ages. A second reason is decrease in pressure, and this happens at divergent plate boundaries. As the plates move apart, the asthenosphere, which is represented in red, starts to rise. And as it rises, the pressure decreases because it's coming closer to the surface. If you recall, this is called decompression melting. A third one is the addition of volatiles, or sometimes we think of it as water. And this occurs at subduction zones. Remember, as a plate subducts, there are materials and water in that downgoing slab that are released and lower the melting temperature of the asthenosphere. Remember, everything red here, asthenosphere, is solid. And this is one way that it can melt. This is also called flux melting. This is a figure also from your textbook, and this summarizes everything that I just talked about. So I want to go through this in a little bit of detail. We have 4 different diagrams showing temperature increasing to the right, and then depth, which is essentially the same as pressure, going on the axis going down here. So in a normal place where there's no melting, we have the geotherm, and if you remember, the geotherm is how the temperature and pressure change as you go into the earth, or in this case, you can think of it as how the temperature increases as you go down. So if you go down to 100 kilometers, the temperature is going to be about 1,000 degrees centigrade. And each of these has a geotherm on them. Then there's the solidus. This is the line at which rocks begin to melt. So this is the pressure temperature conditions necessary to begin melting. And so in normal situations, there's no melting because the solidus is at a much higher temperature than it is inside the earth. At mid-ocean ridges, where we have the decompression melting, the geotherm is significantly changed in its shape. This dotted line shows its original shape, but the pressure decreases greatly. And again, that's because things are moving up to a shallower level, and they cross the solidus. And once those two cross, that's when melting can occur. At hotspots, we actually have a combination of both decompression melting and added heat. So now our geotherm is getting hotter with depth than normal because we have added heat. And it's also a little bit shallower because of the fact that there is material moving to lower pressures. And when it crosses the geotherm, once again, we get melting. Finally, the flux melting at subduction zones is a little different. Here's our original geotherm. You can see it's the same shape as the first one. And in this case, the addition of volatiles to the magma decreases the melting temperature and thus moves the solidus into this position. It used to be here. So this gives you a good summary of where melting occurs and why. Okay, so let's move on to the types of lava. Here's our igneous classification chart, which you're becoming familiar with. And remember that we have phaneritic or coarse-grained and aphanitic or fine-grained igneous rocks. So the volcanic rocks are going to be the ones on the bottom here: rhyolite, andesite, and basalt. So these are the 3 types of lava we're going to talk about. Now, each of these lavas has a different style of eruption. Basalts are rather fluid and sort of gentle, and sometimes that is called effusive. Andesites are quite explosive, and rhyolites are actually catastrophic. And all of this is because of the viscosity of the magma. If you recall, magma viscosity is related to the silica content. So rhyolite, which is the most felsic and has the most silica, is the most viscous, and thus it's kind of the stickiest when it comes to gas being trapped inside of it. And then once that magma reaches the surface as lava, the gas just explodes. So let's look at each of these. Starting with basalts, which again are the low viscosity magma. These flow easily over the ground. And on the left here, this is a place in California called Fossil Falls, where there's a bunch of old basalt flows that are no longer active. There are 2 types of basalt that have names that come from Hawaii. There is A'a, which is this rough, fragmented clinker type of lava and produces some very sharp rocks, which I think is where the name A'a came from. And then we have Pahoehoe, which is this ropey and smooth looking type of basalt. Here's some other flows of basalt. I mean, they certainly are dangerous. You certainly could get killed, but they are not these big, giant, explosive types of eruptions. Here we have the lava actually going into the water, and that's why you see steam. Basalt, remember, is a mafic rock, so it's dark in color and often has these big green crystals of olivine. These kinds of magmas make something called a shield volcano because of the gentle, fluid nature of the way they flow. And this is because if you look at one of these volcanoes in cross-section, it's actually like a warrior shield that's been set on its side. We'll talk more about volcano shapes in the next video. So again, these have effusive or gentle eruptions. And here's a picture of A'a, Pahoehoe. Here's both of them solidified. Here's a Pahoehoe flow. Here's an A'a flow. All of these are slow enough that you can move away from them. This photo is kind of a setup. And there's me from years ago when I went to Hawaii with a class with that student I showed you in the first slide. And here I am indeed using a rock hammer to pick up some very hot lava. So you can't do this with the other kinds of magma, but with basalt you can, if you know what you're doing. Okay, moving on to andesite. Andesite eruptions are probably all of the eruptions that you've heard about in your lifetime that are dangerous. Pinatubo, Mount St. Helens. And these are high viscosity magmas, and so the gases get trapped and they're very explosive. Here are some andesite eruptions. You can see they have very, very large clouds of ash and dust and what's called pyroclastic material. And they often have a lot of the mineral hornblende in them, which is shown in this picture. Here's Mount Rainier, as seen from Seattle, Washington. That's another stratovolcano or andesitic volcano that is active and a real threat to Seattle and the cities in that region. Mount Vesuvius, you may have heard of, was a famous eruption in 79 AD, and it's destroyed the city of Pompeii. Now, rhyolites, the last one, believe it or not, as long as we've been recording history, there's never been a rhyolite eruption. I know that's kind of hard to believe, but we have lots of evidence they exist, but they haven't happened so far. Now here's a computer-generated image of what this eruption might look like, and this was done for a movie about the eruption of Yellowstone, because if Yellowstone erupts again, which it will be a rhyolite eruption. And in fact, I often had my students watch this movie, which now is getting pretty old. I think it's from 2005, and you might be able to find it on the Discovery Channel. It's what do they call a docu-movie? So it's not a documentary, it's a story, but it was made with the assistance of volcanologists and seismologists at Yellowstone. So it's pretty accurate in terms of the science. Anyway, I really recommend this if you're looking for a good thriller movie. It's kind of old, but it's still good and it's very relevant to our class. So rhyolites, because they're so viscous and thick, they tend to come out of the volcano, the lava, and just stop. And so you get what's called a dome or a spine of magma. And then this is tephra, is the material that's been blown on the sides. So rhyolite lavas rarely flow, and instead we get these domes, and the rest of the volcano is usually blown to smithereens. And here's some more examples of tephra cones. And remember that this is a light-colored felsic rock. Okay, coming next, we're going to look at 6 different kinds of volcanoes, and they're going to fall into those 3 compositional categories. And we'll talk more about the shapes and where they happen.